My main goal today is to try to introduce a little bit more precisely what Taylor series are through examples. We'll start with, once again, geometric power series examples. Then we'll use Mathematica to do some computations of other power series that happen to equal some very common functions. Those other power series are actually what we also call Taylor series. It's confusing with all the terminology. I also, as sort of a side highlight in this class, want to justify, in part at least, why 0 factorial is defined to be 1 and how pi can arise as an infinite series. We'll see our first example and even see why it arises as an infinite series. Okay, so let's start with looking at the examples that we looked at on Wednesday. We did look at these examples already on Wednesday. You may prefer just listening, though I'm going to write some stuff in between here that you probably will want to write to some degree. Maybe at least write the final answer here. This function, 3 over 4 plus 5x, does equal this. I'm not going to simplify it, actually, this time. What I instead want to focus on, and I wrote this on Wednesday as well, I do want to focus on both the radius of convergence and the interval of convergence. Write down what they are. Again, I wrote that down on Wednesday, but it's worth writing down again and probably worth you writing down again, because that's the main focus right now, is what is the radius of convergence and what is the interval of convergence. These are geometric series. Not all power series are geometric series. They have to have this form. If it's a series, it's a term, the first term called a, plus a times r, where r is called the common ratio, plus a times r squared, plus a times r cubed, etc. That is the case here. A is 3/4, r is -5/4 x. We already know, we've talked about this many times, the geometric series converges if and only if the absolute value of r is less than 1, which you should always remind yourself means r itself is between -1 and +1, not equal to the endpoints. We need to relate that here to figure out what values of x this converges for. This converges when the absolute value of r is less than 1, but r is -5/4 x. So this converges when -5/4 x is less than 1 in absolute value. You try to rewrite this in terms of the absolute value of x itself. It is a property of absolute values that the absolute value of a product is the product of the absolute values, like this. And of course, the absolute value of -5/4 is +5/4. So I can then multiply both sides by 4/5 to cancel the 5/4 on the left and give me that this converges exactly when the absolute value of x is less than 4/5, which is 0.8. In other words, the interval of convergence goes from -0.8 to +0.8, not including the endpoints. The interval of convergence I'm okay if you write it just with inequalities. X goes between -0.8 and +0.8, which you should also feel comfortable writing as -4/5 to +4/5. In what's called interval notation, you can also write that like this, with parentheses, as if it were a point, but it's not a point. You got to tell from the context that it's not a point. This represents all the numbers on the number line, the real number line, between -0.8 and +0.8, not including the endpoints. And when you draw it, well, first of all, it's centered at 0. The left endpoint is -0.8. The right endpoint is +0.8. Put open circles at the endpoints because we're not including them, and then shade the region in between. Of course, the open circles are kind of an exaggeration. Points have no area. So when I draw open circles, You just need to understand I'm not including the endpoints, but really the interval goes up to, but not including those endpoints. So, for example, 0.799999999, as long as you truncate somewhere, is not equal to 0.8. 0.799999, where the nines repeat forever and ever, is equal to 0.8. You've heard that kind of thing before, but it's true. Decimal representations are not necessarily unique. But anyway, this is just a little bit of a fiction in how I'm drawing it. You just need to understand we're not including the endpoints. Notice the radius of convergence is 0.8 as well. Remember, R is the radius of convergence, is the distance between the center of the interval and either endpoint, whether we include the endpoints or not. In this case, we're not. That's 0.8. That matches what you see right there. It's that distance. This is also 0.8. By the way, it doesn't matter whether you put a 0 in front of the decimal point or not. Sometimes I do, sometimes I don't with this kind of situation. With geometric series that are power series, meaning you've got powers of x, or more generally, powers of x minus something. In the next examples, it's powers of x minus 1. With those kinds of series, you do not include the endpoints in the interval of convergence. However, there are some power series that are powers of x or powers of x minus something, where you do include the endpoints, or maybe one endpoint but not the other. It's weird, but it needs to be thought about and checked. My computer's working extra hard. I don't know why here. Hopefully it will get better. Can I clarify anything there? Here's the other example we looked at on Wednesday. Same function, different power series. It's not centered at 0, it's centered at 1. I got powers of x minus 1. The trick for finding it is a little trickier. It involves an extra first step. First step, replacing x with x minus 1. Here I didn't need to replace x with x minus 1. I just needed to factor out the 4 and write the numerator as 3/4 with a 1 there, minus something, to help me use this. Down here, if I want to expand it as a power series in x minus 1, I need to replace x with x minus 1 first. But if I do that, I have to compensate. By replacing x with x minus 1, I really subtracted 5. So I compensate by adding 5. But then 4 plus 5 is 9. You want that 9 to be a 1, so factor it out and bring it up to the top, and the numerator of the top becomes 3/9. The denominator of the top fraction that you'll get becomes a 9, so the fraction becomes 3/9, which reduces to 1/3. And you're left with 1 plus 5/9 times x minus 1, which you write as 1 minus negative 5/9 times x minus 1. Now it's in the form a over 1 minus r, where this is the r now. So I get a plus a times r plus a times r squared plus a times r cubed. It's a different power series, but it represents the same function. It equals the same function, though the interval of convergence, where both the series converges and equals the function, turns out to be different. For one thing, it's centered at another point, 1 instead of 0. What does that do to the interval of convergence? Let's figure it out. This converges when, again, the absolute value of r, in this case, r is negative 5/9 times x minus 1, is less than 1. Once again, the absolute value of a product is the product of the absolute value. So you get the absolute value of negative 5/9, which is positive 5/9, times the absolute value of x minus 1. After multiplying both sides by 9/5, the interval of convergence is all the values of x that satisfy this inequality. And 9/5 is 1.8. That's the new radius of convergence, 1.8. It's a bigger interval. What is the interval of convergence? Question? Oh, okay. Mm-hmm. Yep, negative 0.8 to positive 2.8. Let's draw the number line first over here. This interval is going to be centered at 1. And what this inequality says is this converges for all values of x whose distance to 1, which is what that represents. The absolute value of the difference of two numbers always represents the distance between them. In this case, on the real number line, but it even works with complex numbers. It's the distance between them. So we're after all the values of x whose distance to 1 is less than 1.8. On the right side, 2.8 is exactly 1.8 units away from 1. And on the left side, go 1.8 units, you'll be at negative 0.8. That's also 1.8 units away from 1. Once again, this series is geometric, so we are not including the endpoints. Make open circles at the endpoints and shade everything in between. With inequalities, we'd write the interval of convergence as negative 0.8 is less than x is less than 2.8. With interval notation, we write that as negative 0.8 to positive 2.8 with parentheses. When you include the endpoints with interval notation, you use square brackets. We will see an example of that still today. Let's do one more example with the same function. Same function, 3 over 4 plus 5x. But now let's expand it about x equals 2 instead of 0 or 1. Same kind of trick as with x equals 1. Replace x with now x minus 2 instead of x minus 1. But then compensate. I'm really subtracting 10. So compensate by adding 10. These functions are equal. Then 4 plus 10 is 14. I'd prefer a 1 there instead of a 14, so factor the 14 out, bring it up top to make the top a 3/14. Then I get a 1 right there. I'd like the plus sign to be a minus sign, so make it a minus as long as you include 2 minus signs. And don't forget to divide 5 by 14 as well, because I factored out a 14 out of both terms in the bottom. These functions look very different, but they're the exact same function. But now I've written it in a way that it's a over 1 minus r. I can see this is the sum of a geometric series, and I can expand the series then. With a, the first term being 3/14. And the common ratio is negative 5/14 times x minus 2. So I get the same kind of thing as before, though it is a different example. It's the same original function, but the series is expanded around a different point. So I get a different looking thing. Don't forget your plus dot dot dots. You don't get full credit unless you remember your plus dot dot dots. We need to emphasize this is an infinite series. That's important. We could simplify this. I won't bother. Let's just say this converges when the absolute value of r again is less than 1, which means in this case, the absolute value of negative 5/14 times x minus 2 is less than 1. And that, through a little bit of work, is equivalent to saying that the absolute value of x minus 2 is less than 14/5, which is 2.8. We keep moving the center of the interval to the right by 1 unit from 0 to 1 to 2. And the radius of convergence keeps increasing by 1 from 0.8 to 1.8 to now 2.8. The interval of convergence, which again I'll draw first, is now centered at 2, has a radius of 2.8. So the right endpoint is 4.8. And the left endpoint is our old friend, negative 0.8. It keeps getting bigger and bigger to the right, but not bigger and bigger to the left. Weird. With inequalities, the interval of convergence looks like this. And with interval notation, it looks like this. Why can't we get past negative 0.8 on the left? What's stopping us? Got a guess? What do you think?
Go right back to the original equation. Negative 0.8.
Yeah. You'd be dividing by 0 when x is negative 0.8, negative 4/5. You get a 4 plus 5 times negative 4/5. This 4 minus 4 is 0. You'd be dividing by 0. This has a vertical asymptote at negative 4/5. 4 plus 5x equaling 0 is equivalent to 5x is negative 4, which is equivalent to x is negative 4/5, negative 0.8. If you graph this function, it's got a vertical asymptote at negative 0.8. Ignore that, draw this here. And the graph turns out to look about like this over here and about like this over here. And for example, the last example we just did, if this is 2 right there, the interval of convergence goes from negative 0.8 to 4.8, not including the endpoints. The interval of convergence does have to be centered at the thing I'm subtracting from x. It's got to be centered there. But its endpoints can't get past vertical asymptotes if you've got one, which will lead to a mystery because some examples don't seem to have vertical asymptotes, but we will sometimes see that the radius of convergence is still finite. And that'll seem strange. We'll even see that example today. I also could have, I didn't, but I could have expanded the series about some number less than negative 0.8, like negative 2 or something, by trying to get powers of x plus 2 instead of x minus 2. X plus 2 is the same as x minus negative 2. That would be expanding the series about negative 2. And if I had done so, it would have equaled the function over here. And for an interval whose right endpoint would have been negative 0.8, not left endpoint. Hope that makes intuitive sense. Can't get past vertical asymptotes. They cause trouble. All right. What I'm about to show you now on Mathematica are some really important examples. You will probably want to write some things down here. We're going to look at some very important functions. E to the x, sine of x, cosine of x, maybe log of x, and a couple others I don't want to mention quite yet, and try to expand them as series. having Mathematica do the work for us with series. What's the syntax? Capital S, series, square bracket, then put the function. Let's start with e to the x. You need a capital E for the number e. Use the lowercase e, it won't work unless you do escape, double E escape, and then it's a fancy looking lowercase e, and that works, but don't do that because you'll probably forget. Use a capital E, comma, curly brace, x, comma, then you put the number that is the center of the interval of convergence for the power series, which means it'll be the number you subtract from x before you raise it to powers. The most common thing to use is 0. That's what I'm going to do here. It's the most common thing to do. Because then you just have powers of x minus 0, which means you have powers of x. Then put another comma, and then you remember you want to put a number representing the highest power of x to show before you see the big O notation. Let's go up to the 10th power of x. N curly brace, square bracket. So this is going to give us, if you're trusting me, a series for e to the x in terms of powers of x. It will be a power series. And because it equals, we think, the function e to the x, we also call it the Taylor series. Taylor series are special kinds of power series. They're constructed in a special way using some given function, in this case, e to the x. I'm not explaining at the moment how this series is constructed. I hope we have time the last 5 to 10 minutes of class to hint at that and trying to get there. What's the answer, Mathematica? Here it is. 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus etc. Plus at the end, it's a big O of x to the 11th. That's Mathematica shorthand for plus dot dot dots with a little more specificities to say the terms that come, the higher order terms, hot, are 11th power and greater. It's not a 0, that's a big O. I could go out to see the 20th power of x as well. Woohoo! Those denominators get pretty big. Do you see a pattern to the denominators of those fractions? The bottoms. You see a pattern to them. Go ahead. They're getting big real fast, you're right. But there's a specific pattern to these numbers that we saw actually on Wednesday. Yeah, 2 times 3 is 6. 4 times 6 is 24. 6 times 4. 24 times 5 is 120. What did we do on Wednesday that's related to what I'm showing you here? Factorials. 2 factorials, 2 times 1 is 2. 3 factorials, 3 times 2 times 1 is 6. 4 factorials, 4 times 3 times 2 times 1 is 24. This is 5 factorial. This is 6 factorial, etc. Evidently, this number is 20 factorial. Mathematica, is it? Yes, it is. This number. But wait a minute. I don't see any fractions with the first 2 terms. Oh, but wait a minute. 1 factorial is 1. X equals x over 1, which is x over 1 factorial. What about the very first term? Yeah, that's why 0 factorial should be defined to be 1, at least one reason. So that this first term in the series for e to the x and some other series is correct. That's the same as x to the 0 over 0 factorial. X to the 0 is 1, right? 0 factorial is 1. Okay, we are ignoring one seemingly large possible fly in the ointment here. We are ignoring the fact that technically speaking, 0 to the 0 power is undefined. X to the 0 over 0 factorial technically only equals 1 when x is not 0, because 0 to the 0 power is technically undefined. Oh boy. So what do we do with that? The answer is we ignore the problem. We just pretend it's not there. I'm serious. Yes, it's a problem that 0 to the 0 factorial is 0 to the 0 power is undefined, but it's a problem for sake of notational ease we ignore. What are we saying here really in that series? We're really saying, evidently, that e to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc. Where yes, this is the same as x over 1 factorial, and this is the same as x to the 0 over 0 factorial, ignoring the complication that 0 to the 0 power is undefined. We are ultimately saying this is true. Now, we haven't done any proofs here at all. We're not proving this at the moment. Will we prove it? Yes, we actually will. We will actually prove that these are equal. How far from now? Well, maybe by probably after Easter, Wednesday or Friday after Easter. It's probably when we will prove that these are equal. No matter what x is. Astonishing. Though it's only equality if you let the pattern go on forever, if you do the infinite series. If you stop it somewhere and do a partial sum, then they're not equal. In fact, if you stop it anywhere, they're only equal when x is 0. How can that be? If you go forever, you catching what I'm saying? If you go forever, they're equal for all x. But if you stop it somewhere, even if you stop it at the millionth power term, they're only equal when x is 0. But they're really close together, close in value when x is close to 0. You had something to add?
At x equals 0, equal 1.
Yep. They're equal when x is 0 for sure. They're both equal to 1. What we can do today, in fact, right now, is we can confirm this series converges for all x. The thing we have to wait until after Easter for is to show that it equals e to the x. If we're going to show this converges for all x, we need to be able to write this series as a summation with a capital sigma notation so that we can see the pattern. It's not a geometric series. This is not geometric. I can't use a over 1 minus r. It does not equal a over 1 minus r for any a and for any r. It's not geometric. But what I can do is I can use the ratio test. It's got factorials after all. Well, let's write it as a summation first. I'll use n as my index of summation. I could use k. Notice the pattern. X to the n over n factorial. For the purposes of the ratio test, that's my a sub n. Now use the ratio test. Take the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by the absolute value of a sub n. In the example from Wednesday with the factorials, all the terms were positive. So we didn't need the absolute value signs. Here, X could be negative, so we definitely need the absolute value signs. They're going to be relevant. A sub n plus 1 is what you get when you replace the n in both spots with n plus 1. The absolute value of a fraction is the ratio of the absolute values, so I can write this. Absolute value of n plus 1 factorial is just n plus 1 factorial. I don't need absolute value signs down there. I'm dividing by the absolute value of a sub n, which means I need to multiply by the reciprocal of this when I include absolute values. The reciprocal will include an n factorial on the top. I can ignore the absolute value signs there because it's positive. And the absolute value of x to the n down here. As we saw on Wednesday, when you've got factorials, this is good because you can cancel. N plus 1 factorial is the same as n plus 1 times n factorial. And so that n factorial cancels with this one. That's a good thing. Something else that's good here is that, well, first of all, the absolute value of x to the n plus 1 is the same as the absolute value of x quantity to the n plus 1 power. Same kind of thing down here. This is the same as the absolute value of x to the n power. And then by properties of exponents, this is the absolute value of x times the absolute value of x to the n, which makes these two things cancel. After you've done those cancellations, it's a lot simpler. It's the absolute value of x divided by n plus 1. What does that limit equal? Can you compute it? What does it equal? Go ahead and say it, Michael. 0. Wait a minute. How can it be 0? There's an x in there. How can it be 0? Because in your mind, you're imagining x to be fixed when you do this calculation. N is the variable. I say this very often. Whether a symbol, a letter is a variable or a constant, it's all in your mind. It's all in how you're thinking about it. Yes, ultimately here, in this equation over here, x will be a variable. We can certainly graph e to the x. We can certainly graph this thing because it equals e to the x. We can certainly even graph partial sums, truncations. They're called Taylor polynomials, in fact, if you do. You can think of x as a variable, but for the purposes of this calculation, to help us decide what values of x this converges for, you think about x as being fixed. Fixed but not specified. N is the variable here. It doesn't matter what x is. It doesn't matter how big it is. It could be a googolplex. This limit's still 0. Once n plus 1 is bigger than a googolplex, then this fraction's already less than 1. And, you know, compared to infinity, and googolplex is tiny. This limit is 0, which is less than 1 for, this is true for all x. Emphasis on the for all x, no matter what x is. What is this telling us? This is telling us the interval of convergence is the set of all possible values of x, all real numbers. Because it doesn't matter what x is. We always get a limit less than 1. The interval of convergence equals, okay, loosely you could say the entire real number line. That's kind of a loose way to say it, because I'm not really emphasizing that the values are real numbers by saying that. It's like I'm saying it's just a line. I mean, that is an interval, but it's really a set of numbers. It's the set of numbers from all real numbers. More commonly, you'd write that with interval notation like this. And by writing that, I'm not saying infinity is a number. I'm just saying the set includes all real numbers. or yes, the funny looking R. In textbooks, sometimes they do make the extra line in there with the funny looking R, or sometimes they just make it boldface. This represents the set of all real numbers. The entire real number line. So what's the radius of convergence? Or we're calling an ordinary looking capital R. Take a guess. Infinity equals infinity. Wait, infinity is not a number. Yeah, we're not treating infinity like a number. And by writing that, I'm still not treating it like a number. It's just shorthand notation to say it converges for all x. It's as if the radius is infinity if you pretended infinity was a number, but we're not in our class. So for us, it's just shorthand to say it converges for all x. Again, none of this proves that it equals e to the x. I'm saying that is true, but I'm not proving that today. We can do it once we get through section 10.4. Which is reminding me, I forgot to do one topic in section 9.4. I forgot to do more with alternating series error bounds. I forgot to do more of that. We'll do more of that on Monday. This is more important for us, though. This is still a power series. Still got powers of x. It's not geometric. Doesn't have the special form of a geometric. We do also call it a Taylor series because it's related to a function in a certain special way that, again, the last 5-10 minutes I hope to show you. All right, that's what the answer is for e to the x. Let's have more fun with Mathematica here. Let's find more series. Why stop at e to the x? How about sine x? Actually, let's go back out to 20. There it is. Huh. Notice it's only odd powers of x for one thing, which means you don't see an x to the 20th power there. Sine's an odd function. There's a deep reason why. You only have odd powers. At least if the series is centered at 0. If it's centered somewhere else, we could get even powers, I'll show you. Signs alternate, plus, minus, plus, minus, plus, minus, plus, minus. Those bottom, so the fractions, hey, they match like e to the x. They're still factorials, aren't they? 50, 40, that's still 7 factorial, just like it is up here. Interesting. Is sine of x related to e to the x? How about cosine of x? Sine and cosine are related to each other, so if sine of x is related to e to the x, then cosine must be as well. All even powers of x, still plus, minus, plus, minus, plus, minus, plus, minus. Still factorials in the bottom. 720 is 6 factorial. Sine and cosine are related at a deep level to e to the x. And this is related to the most beautiful equation in the universe. That e to the I times pi power plus 1 equals 0. What? What is I? I is the imaginary unit. I squared is -1. Pi is pi, E is E. Somehow, this is 0. So in other words, what I'm highlighting here is -1. I claim that the stuff with the series here, the relationships between these series, is one way to prove that. And that is the most beautiful equation in the universe, because it's got the 5 most important numbers in the universe: E, I, pi, 1, and 0, related in a very simple way. What could be more beautiful than that? And physics majors argue, well, those are not the 5 most important numbers in the universe. What about c, the speed of light, or h bar, Planck's constant divided by 2 pi or something like that? Quantum mechanics. And I tell them those are not numbers. Speed of light is not a number. Did you know that? It's not a number. It's a physical constant. Physical constants are not numbers. Did you know that? Like, wait, don't we use numbers for them? Yes, you do, but the numbers you use depends on the units. Use different units, it's a different number. So they're not literal numbers. That's why. Only dimensionless constants are numbers in science. Because when you got units, it affects the numerical quantity that you use. So physical constants are not numbers. Let's do more. What about okay? What about the series for sine, but maybe centered somewhere else? Let's go back to lower powers. Oh, how about somewhere other than 0, like maybe pi/2? All even powers there of not x, but x minus pi/2. But wait a minute, I thought sine was an odd function. This is not contradicting the fact that sine is an odd function. Because you got to look at the expansion about 0 to decide if a function's even, odd, or neither. Not pi/2. Can I do it about pi/3? Then we got a mixture of even and odd powers there. Can I do it about a more ordinary number, like 1 maybe? And now the coefficients involve sine of 1 and cosine of 1, which don't have simple expressions in terms of pi. Are we going to prove all these things? No. Just showing you, you can figure them out. Have Mathematica do it for you. How about another function? Log of x, which again is natural log. If I put 0, though, it's a problem because natural log has a vertical asymptote at 0. But if I put 1, then it's not a problem. I can expand about 1 pretty easily. And the pattern, it looks like, is pretty nice. Signs go plus, minus, plus, minus, plus, minus, and we keep taking 1 and dividing by the next higher number, which matches the power. 3 matches 3. 4 matches 4. That's kind of a nice pattern. How about this one? 1 over 1 plus x squared. Why did I pick that one? I have an ulterior motive. Let's just see what it is. Oops, and let's do it about 0. Pretty simple. Why so simple? One over 1 plus x squared actually has a power series that's geometric. f of x equals 1 over 1 plus x squared. That's the same as 1 over 1 minus negative x squared. And by the way, when you write negative x squared, you're not saying do negative x and then square it. Because if you meant that, you'd write this. It's saying square first, then put the negative sign in there. This is a over 1 minus r. So the answer is, as always, a plus a times r plus a times r squared plus a times r cubed, etc. And that simplifies to 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th, etc. And that's going to converge when the absolute value of r is less than 1. R is negative x squared. The negative sign can be factored out as an absolute value of -1. Of course, that's the same as +1. You can also write this if you like. You can also get rid of those absolute value signs if you like, because x squared and the absolute value of x squared are the same when x is a real number. And you can actually effectively take the square root of both sides here and say this means x itself has to have an absolute value less than 1. X itself has to be between -1 and +1. This is the interval of convergence with a radius of convergence of 1. And if you draw it, centered at 0, radius of 1. Do not include the endpoints because this is geometric. Oops. All right, here comes what I think is the coolest part of the day. What would happen if we integrated this function? Wait, you already know how to integrate 1 over 1 plus x squared. What is the answer? It's a gateway kind of problem. Arctangent of x plus c on the gateway. Could I find the series for arctangent of x by integrating all those terms? Does arctangent of x equal the integral of all that? Question mark. Maybe double question marks, or maybe even 3 question marks. Integrate those. Integrate 1, you get x. Integrate minus x squared, you get minus x cubed over 3. Integrate x to the 4th, get x plus x to the 5th over 5. Integrate negative x to the 6th, get minus x to the 7th over 7. No factorials here. Plus ... plus c. This is bad notation to put a c after the plus ... But guess what? C is 0 because arctangent of 0 is 0. So let's just scratch it out anyway. But is this right? Is this the series for arctangent, and does it equal arctangent? The answer is yes, it does. Here's a confirmation with Mathematica. With arctangent, you do need capital A and a capital T. Of course, again, that's the same as inverse tangent of x. There it is. Same answer I wrote down by hand. You can integrate this series to get this series. Fun. There's our fun for the day. Our biggest barrel of fun. Is this really valid? Can you really do this? Yes, with some conditions, though those conditions are met here. I won't go into details. What's the interval of convergence? You would guess, if you had to guess, if your life depended on it, maybe it should be the same interval of convergence with the same radius of convergence. And that guess would be almost right, but not quite. Let's use the ratio test to see if we can find the interval of convergence almost. We should write this with summation notation to help us. It's a little tricky, but if you look at the pattern, that's how to do it, right? The signs alternate plus, minus, plus, minus, plus, minus. So to take that into account, if I start n equals at 0 instead of 1, I want a -1 to the n power to make that expression 1, then -1, then 1, then -1, then 1, then -1. I want the powers of x that match the denominators to be 1, then 3, then 5, then 7, then 9, all the odd numbers. If I start at 0, this will do that. 2n plus 1 will equal 1 when n is 0. It will equal 3 when n is 1. It will equal 2 when n is 2, or excuse me, 5 when n is 2. It will equal 7 when n is 3. That's the pattern. Let's call this A sub n. Let's use the ratio test. Limit as n goes to infinity of the absolute value of A sub n plus 1 divided by the absolute value of A sub n, when A sub n is this thing. The terms, not the series. No summation signs here. Because I'm taking absolute value signs, or I'm taking absolute values, the -1 to the n power doesn't matter here in the ratio test. It goes away. It just becomes a +1. The 2n plus 1, which will become a 2n plus 3 when n is n plus 1, right? When n is n plus 1, that becomes 2n plus 3. That doesn't need absolute value signs either, because that's positive. The only thing that needs the absolute value signs is the x, because x could be positive or negative. And you can bring the power outside the absolute value signs, just like I showed you before. Effectively, this thing here is the absolute value of an plus 1. And then divide by the absolute value of an, which means multiply by its reciprocal, flip the fraction. You'll get a 2n plus 1 over the absolute value of x to the 2n plus 1. This is the same as the absolute value of x squared times the absolute value of x to the 2n plus 1. And you will get a little cancellation. This will cancel with that completely. So now we are left with the limit as n goes to infinity of the absolute value of x squared. Again, I don't really need absolute value signs there because I'm squaring it. Times 2n plus 1 divided by 2n plus 3. And then here's a key step that could be, you don't have to show this step, but it's probably conceptually clear. Remember, when you do this calculation, you're thinking of x as fixed, n as the variable. So this absolute value of x squared is just a constant. It can be brought out in front of the limit sign like this. And what is this limit equal to? 1. 2 over 2, which is 1. Once again, the degree of the top and the bottom are the same. Look at the ratio of the coefficients of the highest powers of n. Oops, I forgot my square here. So this all simplifies to the absolute value of x squared. The square actually won't matter, though. What does the ratio test say? The ratio test says the series will converge, in fact, absolutely converge. It'll converge even if you took absolute value signs of everything. If and only if this limit starting there ends up in the end being less than 1. Converge if and only if. No, excuse me. Not if and only if. Converge if this is true. Which is equivalent to saying the absolute value of x itself is less than 1. The ratio test also says they will diverge if that's bigger than 1. However, when the limit equals 1, the ratio test gives no information. The series might converge and might diverge. The interval of convergence here seems to be an interval centered at 0 with a radius of 1. But it's not clear, based on the ratio test at least, whether we should include the endpoints or not. So what do? How do you decide whether to include the endpoints or not? You got to think about the original series. Go back here. This series here. When x equals -1, what does the series equal? Replace each x with -1. You'll get -1 plus 1/3 minus 1/5 plus 1/7, etc. When x equals +1, the series will become 1 minus 1/3 plus 1/5 minus 1/7, etc. The opposite of this one, which isn't surprising because arctangent is an odd function. Those two series, this one and this one, actually converge. Think you can give me a reason? Talked about it on Wednesday. It was the thing related to what I said I wanted to do an example of today, but forgot. Alternating series test. Those converge by the alternating series test. I'm not going to show you the details. So the interval of convergence actually includes the endpoints. Fill in the circles. This is the interval of convergence. The closed interval from -1 to 1, in interval notation, use square brackets, not parentheses. The ratio test is not what proves that. The ratio test says converges if this is less than 1, but it's not an if and only if. It could converge when the absolute value of x equals 1, and in fact it does in this case. Though there are other examples where it doesn't. And there are even other examples where it converges at one endpoint, but not the other one. Yeah. You got to check the endpoints separately. You got to think about the original series is the main thing to realize. Do we really care if it converges at the endpoints or not? You might say for approximating functions, it's not a big deal. However, for truth with a big T, It is a big deal for mathematical truth because, for example, if I replace x with 1 in this series for arctangent, replace x with 1 like this, which means I really don't need to include this here because 1 to any power is 1. Let me go ahead and get rid of it. I've got to get arctangent of 1. I'm not proving that, but evidently that's the case. But what is arctangent of 1? You remember? Arctangent of 1. What's an angle whose tangent is 1? In degrees, say. Here's a little hint. "45 degrees. What's that in radians? Pi over 4. The answer involves pi. And in fact, if I go the extra mile and multiply this thing by 4 up top, the answer is pi. A series that equals pi. Fun. Is this a practical way to approximate pi? Turns out, yes, you're right. No, it's not a practical way to approximate pi with partial sums of the series because the series, being actually conditionally convergent, converges very, very, very slowly. However, Newton used other series that converged faster to approximate pi without a calculator. And he computed it, I don't know how many places, maybe 100 places without a calculator. That was the first scientific use of series, was approximating pi to many, many digits without technology. But it has to be a faster converging series than this is, of which there are actually plenty. There's plenty of choices of very fast converging series. To end class today, I'd like to start to try to understand this a little bit better. Why does e to the x equal this infinite series? I'm not going to prove it until after Easter. But even today, in 6 minutes now, we can start to get towards understanding it. We can work towards understanding it. Let's let f of x equal e to the x. Let's let g of x, call it, be, let's say a plus bx plus cx squared. Remember in Calculus 1, you spent a fair amount of time talking about linear approximations. Remember that? Linear approximations, local linearization are different phrases people use. Well, guess what? You can do quadratic approximations too. You can do cubic approximations too, and quartic and quintic and hextic and septic and octic and etc. Octic would be 8th degree. How? Well, you have to say where you're trying to approximate it near, what value of x. How about 0? Use g to approximate f near x equals 0. With linear approximations, you match up the function values and you also match up the values of the derivative at 0. With the quadratic function, you also match up the values of the second derivatives at 0. Now, f of x is e to the x, so it's really nice. F prime of x equals e to the x. F double prime of x equals e to the x. G of x is not too bad either. It's just a quadratic. G prime of x, a, b, and c are constant, so its derivative is b plus 2cx, and its second derivative is a constant 2c. What are these values at 0? The values of these functions. F of 0 is e to the 0 is 1. F prime of 0 is also e to the 0 is 1. And f double prime of 0 is also e to the 0 is 1. G of 0, there's G, plug in x equals 0, get A. G prime of 0, plug in x equals 0 here, get B. And G double prime of 0, plug in 0 here, and well, that's a constant function, you get 2C. Set these things equal to each other and solve for A, B, and C. Guess what? They're real easy to solve. A and B, in fact, are already solved for, and C is almost solved for. 2C is 1, so C is 1/2. And therefore, the quadratic approximation to e to the x near x equals 0, go back up here, A is 1, B is 1, C is 1/2, is 1 plus x plus 1/2 x squared. Hey, that's x to the 0 over 0 factorial plus x to the first over 1 factorial plus x squared over 2 factorial. And guess what? If you did a cubic approximation with d times x cubed, d would be 1/6, 1 over 3 factorial. And if you did a quartic approximation with plus e times x to the fourth, where e is not the number e would be 1 over 24, 1 over 4 factorial. You can try it on your own if you have a burning desire right now. Right away after class even. You could do it. And you would see that these are then quadratic, cubic, quartic approximations, and they are matching partial sums of the infinite series. Think about that. We're matching these functions just at 0. Their values, their derivative values, first, second, third derivative, etc., just at 0, yet in the infinite case, they end up equaling each other for all x. That's astonishing. And yes, it's astonishing enough to take a lot of proof. But again, we will get there in section 10.4. And if you work at it hard enough, you will even be able to understand the proof. Okay, if you understand all the reading in the book. All right, have a good weekend.